everyone to our Lunch and Learn session about graph embeddings. I am Sachin. I am a graph machine learning research engineer at Arango Database. Today, I'm excited to share my knowledge on the concepts of graph embeddings. According to Gartner Top 10 Data and Analytics Trend for 2021, as many as 50% of Gartner client inquiries around the topic of AI, involving a discussion around the use of graph technology. Now, starting with an important question of why graphs are fantastic, we can answer this question in few parts. First, one of the things which make the graph fascinating is its ability to connect isolated data points in space, which is, however, missing in another form of data representations like 2D grid structures used to represent image pixels, 1D sequences used for text, speech, or time series. The second important aspect of graph is that it allows us to store relational knowledge among interacting entities, that is, how different sets of entities are related to each other based on some measure. Now, the representations like 2D grid structures or 1D sequences, except the graph lies in Euclidean space, that is regular unstructured data. And we all know that the well-known method to extract meaningful patterns from the data in the Euclidean domain is convolutional neural networks. However, in the real world, we are surrounded by graph data as well. For example, Internet of Things, 3D point clouds, social network, event graphs, or even chemical molecules, where the nodes represent the real world entities and the edges are associated with the relationship between those entities. Graph as a unique non-Euclidean data structure cannot be operated by CNNs and require a special method to handle its non-regular structures, which led to the recent progress in the area of graph neural networks. In the machine learning universe, graph data structures are exploited by graph neural networks to perform the task of node classification, link prediction, and graph classification. Now, so what is the formal definition of graph? So we can define graph as a data structure made up of nodes and edges. So edges describes a relationship between the two node entities based on some measure. And mathematically, we can define it as a G is equals to V of E, which means the set of vertices and edges present inside the graph. Traditional machine learning on graphs follows a standard machine learning pipeline to extract structural information from graphs. We start with extracting some important graph statistics or features from given graph. For example, it could be node degrees or clustering coefficient. Once these features are extracted manually, we can use them as an input to machine learning classifier, example SVM or logistic regression. On the slide, we can see the node degree features extracted from a given graph and use it as an input to a machine learning classifier. However, there are some caveats of these traditional approaches. That is, they are restricted in nature because these hand-engineered features are inflexible. That is, they cannot adapt during the learning process, and designing these features can be time-consuming and could be an expensive process. So, can we apply convolutional operations on graphs similar to images in order to automate the feature learning? So we know that the convolutional neural networks are designed to operate on regular fixed size data structure, or you can say that data structure which can be represented in Euclidean space. Let's understand the term regularity in data structure with the help of this cat image. So images can be seen as a special type of graph known as the grid graph. Now, applying the convolution in this case means that we examine the neighbors of each pixel by aggregating their values. For example, in this red pixel, one thing to note here is that each pixel in the 2D grid is surrounded by a fixed number of neighbors. So if we move the window from left to right or from top to bottom, the neighborhood size of a target pixel remains the same. However, in the graphs, the neighborhood size of a target node varies. For example, in a social network graphs like Facebook, a very popular person could have millions of connections or neighbors, whereas the normal one can have very few connections. Also, another important point to note here is that in 2D grid, there is a fixed ordering of neighbors, whereas in the graphs, the order of the neighbors of a target node is arbitrary, and this property is known as the permutation invariant property. In the graph convolutional networks, the convolutional-like operation is represented as a two-step process, that is aggregate and update. We aggregate the features from the neighborhood of a node and then update the target node features with these aggregated features. As we have seen, the limitation of applying traditional machine learning on graph is that the hand-engineered features are inflexible. Then the next question comes into mind is finding a way to integrate the information about the graph structure. For example, information about nodes' global position in the graph or its local neighborhood structure into a machine learning model. To tackle this problem, representation learning approaches have been adopted to encode the structural information about the graph into the Euclidean space, or also known as the vector or embedding space. So the key idea behind the graph representation learning is to learn a mapping function that embed nodes or entire subgraphs as points in low-dimensional vector space, or also known as the embedding space. So here the aim is to optimize this mapping so that the nodes which are nearby in the network, in the original network, should also remain close to each other in the embedding space while pushing apart the unconnected nodes. Therefore, by doing this, what we can achieve is that we can preserve the geometric relationship of the original network inside the embedding space by learning a mapping function. So the two key components here are, number one is the encoder, which maps a node to a low dimensional vector. And the second one is the similarity function, which defines how the relationships in the input network maps to relationships in the embedding space. So here the similarity function could be, for example, cosine or Euclidean distance, depending upon his or her choice. Now let's understand the concept of graph representation learning more intuitively with an interesting example from the graph structure of Zachary Karate Club social network. So in this graph, the node represents the person and there exists an edge between the two persons if they are friends. So the coloring in the graph represent different communities. In the figure A, we can see this Zachary Karate Club social network, and figure B illustrates its corresponding 2D visualizations of node embeddings created from the deep work algorithm, which is one of the graph representation learning methods. If you analyze both of these diagrams, you will find that the mapping of nodes from a graph structure to an embedding space, which is represented as a figure B, is learned in such a manner that the distances between the nodes in the embedding space mirrors closeness in the original graph, which means that we are preserving the structure of the node's neighborhood. For example, the community of the people marked as violet and green shares close proximity in the 2D space compared to the communities violets and sea green, which are far away from each other in the network, which means that, which is similar to what is there in the karate graph. So here, what this both of these diagram is implying that we are preserving the geometric relationship which is there in the graph, and the same geometric relationship is also being preserved in this embedding space. So once these node embeddings are generated, what we can do is that we can use them for various machine learning downstream tasks. Number one is that we can use as these embeddings as a feature inputs for downstream ML tasks. Example, community detection via node classification or link prediction. We could also construct a case KNN or cosine similarity graph from embeddings. The graph could be used to make recommendations, example, product recommendation. The third application which we can perform with these generated embedding is that visual exploration of data by reducing these embeddings to 2 or 3 dimensions using UMAP or Disney algorithm. And another application where these embeddings could be helpful is the dataset comparisons and even transfer learning. So this slide shows the embedding visualization of Amazon product recommendation dataset at 3 different layers of graph stage. So about this graph dataset, so in this graph, in this Amazon product recommendation graph, the node represents the Amazon products and the edges between the 2 products indicate products purchased together. So whenever the 2 products are purchased together, then there is an edge. So basically edge is drawn between those products. So this is how this Amazon product recommendation dataset is created. So based on the co-occurrence or of the 2 products. So the node embeddings visualization at layer 1 shows that the model is not able to separate the product categories well, as the embeddings of different product categories are very close together. Therefore, we cannot predict or estimate with a high probability which 2 products can be bought together in the future, or if someone buys one product, then which other product he or she also might be interested. So for each, so for performing the experiments, I have used the graph sage algorithm, which is an inductive graph representation learning algorithm. And then, so this is the visualization of node embeddings at the second layer of graph sage. As we can see now we can see some separate clusters of product categories, and we can draw some valuable insights from these clusters. For example, this cluster C1 is representing movies and TVs versus CDs and vinyl, and the cluster 2 representing grocery and government food versus health and personal care. So it means that these 2 products are very close together in this embedding space, which means that in the original network, these 2 products are also very close as well, which is making sense, because if in case you buy a grocery or any government food, then there is highly likely chance that you will also buy a health or personal care product. So it's similar is the case with this, the third cluster, which is representing video games versus toys and games. And then this is the last layer representation, or the layer 3 represent node embeddings visualization of at the layer 3, in which the node representations are little more finer than the layer 2, and we can also see here some more distant clusters like C1 cluster representing cell phones and accessories versus the electronics. And then there is this cluster 2, movies and TVs versus CDs and vinyls, and same as in the, which is same as in layer 2. And then we have this third cluster, beauty versus health and personal care. So which implies that from these embedding is that, so there is a highly likely chance, so the distance between these products or these data points implies that there is highly likely chance that these two products are bought together. And yeah, and if anyone wonders how I have created these visualization of node embeddings, then I have already prepared a Google Colab notebook with which you can play around and yeah, and perform a lot of experiments by using, by adding some more layers in the graph stage or performing some more hyperparameter tuning in order to increase the accuracy of results. So the end note here is that I hope everyone enjoyed this lunch and learn session about the quick introduction towards graph embeddings and its application. See you next time. Thank you very much.